So yeah, number 21 is a typo. It's okay.
And then 41,
41.
it's asking about penetration and shielding. I don't really understand like penetration and shielding.
Okay, 41 we're going to talk about today. Actually, this is chapter 9.
Oh, okay.
Oxygen has an unexpectedly lower ionization energy than nitrogen because of penetration and shielding. This is actually false.
I'd say, wouldn't that be false because it's smaller, more compact, higher energy?
Yeah. The one thing is you expect to have a higher, but because of Z effective. But we'll talk about it.
And then 42 as well. Are we going to talk more about Z?
Yeah, we're going to talk about this today. This is actually applications of quantum. And so we'll talk about 40, 41, 42 today.
I was about to ask for 40. What does AR in front of for us to?
AR just means the electron configuration up to argon.
Okay.
And so it would be 1s2, 2s22, 2p6, 3s22, 3p6. This is abbreviation, shorthand.
Is that one B8?
What? I'm sorry?
For 40, is it 8?
How many valence electrons does it have? It's actually, no, it's not 8. It's 2. It has 2 valence electrons because the n equals 4, when we look at quantum mechanics or we look at the Bohr model, what would the fourth radius be? It would be 16 times 0.54 angstroms. It's n squared or 0 or n squared or 1, whatever I call it. I think I call it n squared or 1. Our book calls it A0. But anyway, it's going to be 2 n squared times the first radius, which is 0.54 angstroms. And so that would be the radius. It would be 16 times 0.5, so about 8 angstroms out from the nucleus.
Wait, yeah, 8.6.
Yeah, that would be better. And then if it's n equals 3, how many times? It would be 9 times.
Yeah.
So what's 9 times
4.6.
Yeah. So one would be 4 angstroms. The other would be 8 angstroms. So an n equals 3 is 4 angstroms away from the nucleus, and n equals 4 is 8 angstroms away from the nucleus. And so it's like twice as far from the nucleus. And so if you're an oxidizer, you're looking for the outermost electrons. The outermost electrons will be this. But once the outermost electrons are gone, then the oxidizer will try to take the inner electrons. So we call these the inner. These were the inner electrons. Now they're the outer electrons. But initially, and I'll talk about the definition of valence. We have a very specific definition of valence. Valence electrons are the electrons in the highest n. The highest n. It's weird because you would think that the valence electrons would be the ones with the highest energy. But it turns out it's not. The valence electrons are going to be the ones that are furthest from the nucleus. And so there are 2 important applications for this, basically. And one is the transition metals. So the transition metals always screw people up. So let's look at some transition metals like iron. If we look at iron, we look at how many total electrons it has. It has 26 electrons. And then we just fill it. It's multi-electron, so we start at 1s, then go to 2s, and then 2p. And then 3s, and then 3p. So up to here, I filled my first shell, which is helium. I filled my second shell, which is neon, and I filled my third shell, which is argon. So what some people do is they abbreviate all this as argon. So we call it the argon core. So this is the argon core, which consists of all these shells, the first three shells. Right. Right. Exactly. And so normally when you separate the core electrons from the valence electrons, well, the valence electrons are tricky for the transition metals, and also one other group, and that's the fourth period and lower main group elements. And I'll talk about that in a minute. And so what we have, the next orbital after 3p is what? 4s. And 2 electrons there. And then after the 4s comes the 3D. And so the thinking here is we want to ionize the highest energy. So this is 18, 19, 20, 21, 22, 23, 24, 25, 26. That takes care of 26 electrons. And then the 4p are empty. So there are no electrons in the 4p. All of these orbitals are going to have, I arrange them like this. So these ones are going to be the N00 orbitals. And so we have the 100, the 200, 300, 400. And then for the P's, we're going to have the N1, negative 1, the N10, and the N11. And so it just varies by the number. And then the D's are going to be the N2, negative 2, the N2, negative 1, the N2, 0, and the N2, 1. Yeah. And so, it's 3D, 4D, 5D, 6D, etc.
6 valence left.
You would think, the highest energy would be the easiest ones to ionize because they're going to have the shortest jump here. And that's correct. They would have a shorter jump. It would take less energy to ionize them. However, they're less accessible. So if you're an oxidizer, you're approaching an iron atom, you're going to take what's closest to you. And what's going to be the closest to you? It's going to be the 4s. But if the 4s is that far from the nucleus, the 4s, because what we did is we talked about the most probable distance, right? The most probable distance is going in the hydrogen atom is going to be the same as the Bohr orbit, pretty much. Yeah. And now that's the hydrogen atom is only one, and this is multi-electron, so I'm just guesstimating. The distance is going to be n squared, which is correct, 16 versus 9. So this is going to be 16 times further from the nucleus, and this is going to be 9 times further from the nucleus. So what we're going to do is we're going to ionize the electrons that are farthest from the nucleus first. Now, the question comes up, why is it that this electron is farther from the nucleus but lower in energy? Isn't it the farther you get from the nucleus, the higher the energy? Yes, that's the case. You would expect that. However, when we look at the shape of a 4s probability distribution versus a 3D probability distribution, in fact, we can take a look at that here. So, do you know what the Schrodinger equation looks like?
No. We did not go over how it works.
Let's take a look at the Schrodinger equation here. This energy comes out from the Schrodinger equation here for single electron. Multi-electron, the energy depends on two things. So we'll take a look at that. This is a Schrodinger equation here. It's usually in this form right here on the bottom. Or this form here. No, you don't need to know this. If you've had calculus, if you've had linear equations, it's not difficult to solve the Schrodinger equation. You know, you could just do this with basic calculus and pen and paper for the hydrogen atom. Anything more complicated than hydrogen atom, you can't do it easily. And so from the Schrodinger equation, we can get the energies for the electron, but there are many energies that are allowed. There are infinite number. So you aren't going to list an infinite number of energies. What you want to do is you want to list a pattern. And so in other words, what they do is they list the answers like this. These are the wave functions. The wave functions are going to have what we call the radial part here, and then there's going to be an energy part. The radial part just tells us the shape of the wave function, the real wave function. Angular wave function. And so this goes through the solutions to the Schrodinger equation. The solution, now if we look at this here, these are the answers, but we need to know what R is and what Y is. So what is R, what is Y? Those parts to it. And so we come up with this. Oh, not right there yet. We come up with this. These are the answers. So here's the R and here's the Y. That's a lot of answers. You know, there's going to be an infinite number of answers. Since there are infinite number of answers, the easiest thing is just to come up with a generic equation and then just change what changes in each of these. And what changes in each of these is the quantum numbers, n, l, and m. So n and l and m come from the mathematical restrictions of this. We're not actually going to do this, but you could do this if you just have some calculus in the background. So once we get the Schrodinger equation, we don't want to think in terms of individual answers. We want to look at the pattern in the answers. And the pattern in the answers is going to be defined by n, l, and m, and then we're going to memorize some stuff so we don't have to calculate it. Because when you calculate, when you see something like this, what is the shape? Can you tell what the shape is by looking at that equation?
Yeah.
Well, you could, you know, you've got to plot it out, but I can't either. I mean, I look at that and I don't know what the shape looks like, but
Can't do that.
But we can, and so it's easier to memorize. Isn't it easier to memorize an S, the shape of an S orbital, or the shape of a p orbital, than to look at the equation and then just try to draw it? But when one of the homework problems asks you to draw the shape of the p orbital, I don't know if you guys will have to do the homework, but it does it by the polar coordinate. Here's the origin, and then doing this kind of thing. You don't have to do any of the math. You know, the shape is, okay, I don't want to do the math. I just want to know the shape is something like that. So you could do the math. You get to see it. And there's one homework problem where if you wanted, and we're so inclined to plot it out, you could plot it out because that comes from the Schrodinger equation. But what's much easier is to memorize these quantum numbers. You know, the quantum numbers n, the principal quantum number tells us for single electron, this is the energy level. For multi-electron, the energy depends on primarily N and secondarily on L. And so for multi-electron, the energy depends primarily on N, the energy level, and secondarily on L because L, depending on the shape, tells us how penetrating that orbital is. And the more penetrating the orbital is, you know, 0 are the most, those are S, followed by P, D, F, G, H, etc. It becomes less and less penetrating. And therefore, the higher the L, the higher the energy. The lower the L, the lower the energy because it's more penetrating. And so for multi-electron, we have two things that the energy depends on. And this is why we get two different diagrams. The S and the P and the D split. So that's what gives us that. And the M sub L's tell us the number and orientation of the orbitals. And so we have N, L, and M. So it's much easier to deal with N, L, and M. So this is just going through them. But there are other characteristics. So this is single electron, an energy level diagram. A single electron energy level diagram, the energy only depends on N, not L. So we'd have two different L's, and L equals 0 and L equals 1. They have the same energy. It's because there's no shielding. And so for multi-electron, we have to look at shielding. So this next part is going to look at shielding here above. Okay. So these are different types of wave functions here. You can see the S here, so like a P and an S. So this is the 2S here, and this is the 2P here, dash. And then we have the 3S. The 3S is the most penetrating. Do you see? There's a much higher probability it's closer to 0. If we compare the S and the P here, the P is a lot less penetrating. S. This is not the probability. This is the actual wave function. Well, the actual wave function can have positive amplitude and negative amplitude with P, but for the probability, we square it. But still, you can see that the S is going to have greater probability close to the nucleus. And then here's the D. Do you see the D's are the short dashed lines here? Are the D orbitals very penetrating? No, not at all. So the D orbitals aren't very penetrating. And so even though the D orbitals, the electrons we expect to reside closer to the nucleus, the 4s are much more penetrating because the 4s are going to be lower in energy. However, there's good probability that the 4s are going to be a lot farther from the nucleus. Because what we can look at is the distance here. Take a look at the distances. Yeah, this is going from 0 to 5. Actually, let's look at the squared, the probability. So a lot of this math we're skipping, but it's good to have the math here as a reference in case you ever have to calculate something. Nice to see it presented. Steps. So these are the shapes. So it was asking you to make a plot of the p orbital. You don't have to actually do it. These are the d orbitals. The d orbitals, do you see the plus or minus? Plus or minus because they can't show you the amplitude. Yeah, it's going up and down. That's why we do that. Yeah, right. 3-dimensional, you can't do it on 2D. So
it'd be easier with like a little model kit.
Right. So that's why they color code and label. Color code is blue for positive, red for negative. That makes sense.
Oh, that's nice.
So here's the 1s orbital. energy is a different calculation. But the wave function should contain all the information. Here's the wave function in 3D. Plot the amplitude here. Map it out. And then this one we don't really have to square it, but we can square it. This gives us a probability distribution in 3D there. Electron probability density distribution. Not much. I mean, these you can generate. In fact, we had software. We can generate this quite easily. The software is called. Let's see if they put it on here. So it's supposed to be on here, but it's not. It's all right.
For figure 826, those three represent the first, second, third S layers of wave path, right?
Right.
Is it purely spherical or is it
It's spherical. This is the 1s, 95% boundary. This is not 1s in here. This is actually 2s. This is a positive amplitude, and 2s is a negative amplitude of 2s. So the 95% probability boundary for 2s is out here. But there's a node between the blue and the red where there's zero probability.
There's nothing there.
Yeah. Right. There's going to be n-1 internal node. So this one doesn't have any internal nodes. This one has one internal node. A 3s has two internal nodes. So it goes positive amplitude, negative amplitude, back to positive amplitude. And so it's going to be a wave like this.
So when a node exists in the electron cloud, does that act as the forbidden area of the energy level?
Yes. I mean, it's forbidden area for position. You aren't going to find the electron. So the electron's kind of weird because how does it get from here inside the blue zone into the red zone without ever being found in the node zone? How does that happen?
A little bit of hopscotch.
It doesn't happen for a particle unless, but if it's a wave, then yeah, it can happen. The wave can be here with positive and it can be here with negative and go through zero. With a wave that can happen, but with a particle, it's weird to think about.
My theory, the electron is moving so fast it's phasing in and out of space.
Okay.
It's effectively becoming and not becoming.
Here's the p orbital. P orbitals are a lot less penetrating. You see? I mean, there's no probability here at the nucleus. The psi squared versus an s orbital where there's good probability. So s orbitals are much more penetrating. Here, there's good probabilities right at the nucleus if we look at the density. In fact, the highest probability is right at the nucleus for an s orbital.
So what does penetrating mean? It's the opposite of shielded, right?
Right. It's penetrating means it's constantly shielded. The argon core is shielding the nucleus. Each filled core is spherical. So if I combine all the S and the P, that's a shell. So this is why we call it a shell, because this whole thing mimics like a sphere around it. And so the 1s are shielding, the 2s and the 2p are shielding, that's another shell. And then the 3s and the 3p is another shell that's shielding. So all these are shielding, but they don't shield evenly because the shielding is steady, constant. This is always being shielded by these three shells. What can happen is the 4s, there's some probability it can sneak in and get close to the nucleus. And there's some probability that 3D can sneak in and get close to the nucleus. So even though you have all these electrons blocking the charge, this electron might sneak around and be found closer to the nucleus. Does that make sense? That's penetration. And penetration is just simply looking. If a p orbital sneaks in and tries to get close to the nucleus, how close can it get? Well, you can't. Can it get all the way to the nucleus? No. And so that means the p orbital can only make it, let's say, this far. But then we compare it to an s. When we look at an s electron, yeah, an s electron can get right on top of the nucleus because there's probability that s is there. And it doesn't matter if it's a 1s, a 2s, or a 3s. They all have that probability. The highest probability is going to be at the nucleus for all of these. And so that means an S can sneak around and be right against the nucleus. If it's right against the nucleus, then nobody can shield it. Because all these other electrons are shielding it. And so that's what penetration refers to. You know, what is the probability that the S electron can be close to the nucleus versus a D electron? They're different probability. The probability that the D electron can be close to the nucleus is, we don't have a fancy 3D graph for this.
But we have those small little
But we have, no, we do have a fancy 3D graph for this. I thought we didn't. So what is the probability it's going to be very close to the nucleus? Well, this is the wave function. So we have positive and negative amplitude. What we need is psi squared. Do we have a psi squared?
Let's say go one more page.
Let's go one more page over. And unfortunately, we don't have a psi squared. But this is good enough. Here, this is a 4D, but the D's, you know, the probability that they're going to be close to the nucleus. Let's see if I can go back. We go back to graph of the wave function here.
For psi squared.
No, just for psi. I'd like psi squared. It would be better to have psi squared, but since we only have psi, we'll just deal with psi and then imagine squaring it. So the D, do you see the D is the short dashed line here?
Yeah.
What is the probability it's going to be close to the nucleus? Very low. Do you see that?
Yeah.
Compared to the S. If you look at the 3S has much greater probability. So which one's the most penetrating?
S.
The S, followed by the P, followed by the T. So this is the reason.
So it goes in order.
Right.
Just, well, almost in order.
It goes in order. For a given n.
Yeah.
For a given n, it goes in order. And so we see the same thing here. The S is the most penetrating, followed by the P. There's no 2D. And the same thing would happen with the S. You know, the S would be even less penetrating.
So n equals will determine our penetration.
Right. But if there's no shielding, does it make any difference?
No.
No, if there's no shielding, then it doesn't make any difference because all these have the same effective distance. So if there's no shielding, then these all have the same energy. And that's why the Bohr model worked for one electron species, but wouldn't work for multi-electron because Bohr didn't factor in. Well, Bohr didn't know about all these different shapes.
So for these graphs, what's the x-axis and what's the y-axis?
The x-axis is the distance from the radius. And the y-axis is the amplitude. That is how big the wave is at that particular point. Here, when it goes through zero, there's zero amplitude. Now this is psi, the wave function. Psi. This is actually the radial part of the wave function psi, but essentially this is psi. And so if we were to square this, then we get the probability. You know, we can't have negative probability, so that's why we have to square the probability. But this is just the shape of the orbital. This is the shape of the orbital in a cross section. And so all we're doing is looking at the shape, but it's a little bit more than the shape because it's indicating how intense, you know, that is, what the probability is for finding it at certain distances from the nucleus. That's penetration and shielding.
One last question for this. In terms of penetration, when you say hypothetically a 4S goes directly to the nucleus, how does that affect the other electrons? Will something be promoted?
No. No,
Or is it just existing right there?
it's just existing. In one instant of time, it's there. In the next instant of time, it's somewhere else.
Okay.
It's like a bird.
Oh, so it's in terms of the movement. So
Right. The movement is just random. You can't exactly predict where the electron Could you predict where the bird's gonna be next month? No. I mean, the same thing with electrons. A bird, electrons like a bird. Although maybe it's deterministic. Some people are saying it is deterministic. They can predict where the electron's going to be. You know, so that means they can predict where the bird's going to be in the next month. You know.
Let's see that.
Yeah, let's see how they predict it.
I was curious.
Then you could predict the future. You could set up a booth or something. You can predict it. Yeah.
Just make a show out of it with like the whole line of cards, right, and a glass ball.
Yeah.
Go as far as possible.
Actually, predict where the what is that? The Powerball balls are gonna. Which one? Let me tell me.
I was just curious to think that if a 4S was a cell electron pair, would to force itself basically down to the nucleus, would every other S have to bump up for a new 4S to take its place just to repeat?
No. The 4S is not taking the place of anything. Right, the 4S is just moving around, and what we have is a probability distribution. You know what a 4S, the electron count for 4S looks like is, well, let's look at the wave function for 4S. So a wave function for the 4S orbital, psi versus the distance, radius, is going to look like this. It's going to have n equals 4 has how many nodes? Nodes. Internal nodes. 3. So it's going to cross 1, twice, 3 times. That would be a 4S. And then what we do is we square it to get the probability. So when we square it, it's going to go like this.
No.
Starting point
Yeah, and so the electron might be here, or it might be here, or it might be here. It doesn't matter, it's still a 4S electron.
Okay.
It's got probability it could be anywhere. So most of the time, maybe the most probable distance is out here, but sometimes it's going to be right here, next to the nucleus. That's penetration.
Sometimes it looks very similar with 2S.
Mr. Sherrod,
Yeah.
how do you project how many nodes?
There are n minus 1 nodes,
Oh,
internal nodes. N minus 1 internal node. So these are the 3D orbitals here. So how many nodes are we going to have for 3D? 2. We have different kinds of nodes. If we look at s orbitals, the nodes in s orbitals are called spherical nodes because those radiate out in 3 dimensions. So let's take a look at the spherical nodes here. So this is a 3s, and we should have how many nodes for 3s? 2. So we start off positive, go to negative, that's 1 node. Go to positive, that's 2 nodes, and then stay there. And so we go positive to negative to positive, and then stay positive. So the wave looks like that on one side. But, you know, this is in 3 dimensions. We're just looking from the origin out. And then we do this in 3 dimensions. These come out to be spherical nodes. This would be a 4S with 3 nodes. And, so we'd have 3 things like that. Those are called spherical nodes. Then we have planar nodes. So a 2p, how many nodes would a 2p have? 1. So it goes here, it's positive, then goes to negative. There's your 1 node. It's got to go through 0. So it's positive, goes to negative, you got the 1 node. This 1 node is called a planar node. It's not a spherical node, it's a planar node. And we can see that here in the next figure. These are the planar nodes. And here the gray planes. And there's going to be a node there because it's going from positive amplitude to negative amplitude. Could be a node.
So it would be the same with 2S?
This is 2s here. Oh, no, sorry. It would be the same with 2s. that is the number of nodes, but it would be a spherical node. This is 2s, it would have one node, so you're going positive to negative and staying negative. And so the node's here where it goes through 0. That's a spherical node. S orbitals have spherical nodes. P orbitals have planar nodes. So P orbitals have planar nodes here, like this. Now, D orbitals have planar nodes as well, and something called a conical node. So D orbitals have how many? This is 3D, so how many nodes? 2. So this is showing 2 planar nodes, slice, slice. And so positive, negative kind of amplitude. You can see it. You know? It's going to be changing because it's a wave. So we're going to see this. This is like the plate, you know, the plate.
It's going to keep moving because it's violently energetic.
And a positive and negative amplitude. And so this is 2 planar nodes, slice, 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 slice. This is not, do you know what this is called? A conical node or cone node. And so we have one cone node here and one cone node here. These two conical nodes. This is a really weird shape. It's like a p orbital with a hula hoop. And it goes positive and then negative. It's a weird shape, but you have weird shapes. Even in 2D wave functions, they're weird shapes, aren't there? Oh. Those look very weird, but it's just, you can tell. All right, this is a 3PZ. If we're looking at a 3PZ, 3 is how many nodes? 2 nodes. Now we have a planar node here, and then we have a spherical node here. And so it's weird how it's like, you know, positive, negative, positive, negative. It's kind of weird in that sense. And then over here, this is 4D. How many nodes do we have?
3.
We have 3 nodes. So we're going to have planar node, spherical node. Chop it up. It just helps us kind of visualize the wave, you know, kind of thing. We see the positive and the negative and the nodes. You know, we can see the complexity of the wave function. Yeah. This is the magnetic spin number here. But you know, I forgot that chapter 9 is kind of an application. This is taking silver atoms. This is a very famous experiment. This is called the Stern-Gerlach experiment. The Stern-Gerlach experiment was critical in determining that the spin quantum number for electrons. And so this is, in fact, they won the Nobel Prize for this. Stern-Gerlach.
And that was for electron spin.
Electron spin. There are only 2 spin states, plus 1/2, minus 1/2. Why odd numbers? It's because of the algebra. You know, basically we get an algebraic equation from the Schrodinger equation, and it's the algebra there. Now, different books use different labels. You know, N, L are pretty standard. I use L here rather than M sub L. This is M sub L, a lot of people use that, and M sub F. But I just call it NLMS. M sub L. M sub L is because M sub L depends on L. And so maybe I should use that instead. Are these quantum numbers okay? This one's not okay. What's wrong with that one?
The spin.
The spin can't be 0. Is this one okay?
No.
This one's not okay because this is a 2-0, which is a 2s, but we only have one of those. You know, if L is 1, then we should have a 1, 0, negative 1. But we can't win that. And so this is not possible, right? Yeah. So that's not okay. How about this one?
Yeah.
The L is wrong. It's too big. This is a 2D orbital. There's no such thing as a 2D orbital. And what's wrong with this one? That was wrong. There's no such thing as -1. There's no such thing, meaning it doesn't solve the Schrodinger equation. You can try plugging it in, but it's not going to work. You're going to get some nonsensical answer. And so, how about the last one?
That's fine.
Yeah.
It's okay.
Yeah, that one's good. So we just, if we know the patterns, and that's pretty much what we're going to use. In fact, a lot of the mathematics of quantum mechanics, you don't do the grinding math there. You just do these simple things where, like little patterns like this. How about number 3? I mean, this one, 3, 2, -2, 1. Is that okay?
No, this
No, spin. This one?
Yeah.
Yeah. No, was it Amsterdam?
Yeah, right. I call this M. So N and L are okay. This would be a 3p orbital. But is there -2 for a 3p orbital? No. How about this one?
Yeah.
Yeah, this is a 3s orbital, no problem. The electrons spin out. This one?
Oh,
No, this would be a 2f orbital. 2f orbital doesn't exist. How about this one? This one's fine. 1s orbital spin down. How about this one?
L.
There's no such thing as -1. Okay, that's good. Well, I guess you know what I'm going to do is, so you should know this, right? And the difference in diagram between single electron like hydrogen and multi-electron like everything else. Why do you think the 1s is lower for multi-electron than hydrogen?
It's a lower energy, so the first valence would be farther away. Wait, no, that wouldn't make sense. It's closer.
It's closer, meaning the 1s orbital. Which one's smaller? Which one has a smaller 1s orbital? Multi-electron or hydrogen?
No, multi-electron has a smaller one.
Why does it have a
Higher positive charge.
yeah, multiple protons. It has a higher positive charge. This is why it's lower in energy in general. And the more positive charge, the lower the energy. The less positive charge, the higher the energy, the bigger, the smaller. And so they aren't fixed size and fixed energy. Now, this is all relative. We could actually calculate the energies in the Schrodinger equation.
You say that they're dependent.
We don't really use the path dependent stuff here, but
No, only for was it employees.
okay, then we got into penetration and shielding. For penetration and shielding, I'd like to use the radial distribution function. The radial distribution function is that green line I did yesterday, I think it was.
Find it R².
Remember that? Where you divide the cloud into onion layers, and then you count the number of dots, and then you see which one has the greatest number of dots, and then we plot that out. That's called a radial distribution function. And so let's see if they plotted it out. Yes, they did plot it out. And so the greatest number of dots is here. The greatest number of dots is here. And so we could use different things. We could just use the wave function to show which one's more penetrating. We can use the probability function psi squared to see which one's more, or we could use the radial distribution. The radial distribution function is very useful. It's called the RDF, radial distribution function. These are very common. And the RDF can easily show us how penetrating these are. So this is an s orbital, the 1s orbital. Is it very penetrating?
Yeah.
Yes. It's very penetrating because the radial distribution function doesn't look like the wave function. The wave function is going to have the greatest probability right at the nucleus, right? But we know the onion shell right at the nucleus is very small volume. And so this is better actually because this tells us, how many dots are here. And this is not that big, but in terms of the most probable distance, where is it? Well, it's about 0.54 angstroms. It's about a half an angstrom. This is in angstroms here. Yeah, radius relative to A naught. What is, actually radius relative to A naught, one would be 1 A naught, which would be 0.54 angstroms for this.
What is A naught defined as?
A naught is the first. A naught in terms of Bohr would be the R1 in terms of Bohr. And so, but it depends on what Z is, because Z is going to change that. And so it's the first orbit or the first, well, let's say, is the most probable distance. So the most probable distance we'll call 1 here. And that's going to be normalized by A naught. So I wouldn't worry about it too much.
It's called A naught instead of A of 0.
A naught is just a reference
Okay.
point. Usually they'll call it some kind of reference point. They call it A naught. Then A naught, you're saying why don't they just call it A sub 0? I don't know. No, I think it came from the UK. Yeah, the whole naught thing, naught is being 0.
Reminds me of knots, like in the water.
Well, let's continue here. Okay, so the 1s is very penetrating. Let's compare 2s and 2p. The 1s are going to shield. You see how they're shielding? So this is about 1. So we have this big hump here from 1s right here. And the 1s are going to shield the 2s from the nuclear charge. Can you see that?
Yeah.
Because we got this big hump here that's going to peak at 1. And it's also going to shield the 2p. And which one do you think it'll more effectively shield, the 2s or the 2p? The 2p. Because you see this blip here?
Yeah.
There's pretty good probability that the electron can be right close to the nucleus. Does that make sense?
Yeah.
All right. And then you can see it here, 3s, which of these are the most penetrating? Which is going to have some probability of being found closest to the nucleus?
3s.
Yeah, the 3s, we have this little blip here, which is missing here. And we definitely don't have it here with the 3D. The 3D are the least penetrating, followed by the 3P and the 3S.
Which means that 3D would be the most shielded.
The most shielded, right. The most shielded, because the 3D are going to be shielded by the 1S, the 2S, and 2P, and the 3S and the 3P. These are all going to be blocking the 3D. But however, the most effective blocking comes from the inner electrons. The 1S and 2S and 2P are shielding pretty much 1 for 1. That is, for every electron in the inner shell, it pretty much blocks 1 positive charge from the nucleus. But these are called same shell. 3s and 3p are the same shell. 3d are the next shell. But 3s and the 3p are the same shell. Same shell electrons don't effectively block. So the 3s here aren't really effective blockers of 3p. There's actually, you can actually calculate this in quantum mechanics, how effective a same shell electron is versus an inner shell electron. And there's a homework problem assigned for that too. And so we'll look at it. We can come up with a rough qualitative calculation for this. And that rough qualitative calculation is called the calculation for Z effective. Z effective is the effective nuclear charge. The effective nuclear charge is the amount of charge the electrons see from the nucleus, factoring in shielding. And we have some simple equations for Z effective if we want to approximate it. You know, that is, we don't need something super accurate. And we'll take a look at that calculation too. All right. Basically, then we talked about figuring out the multi-electron shells, and we use this pyramid. And we talked about Hund's rule and different things. And so I want to talk about this. There are different ways of representing this. What was this diagram called here? Yes. This is the energy level diagram, or the atomic orbital energy level diagram. And so the complete name would be the atomic orbital energy level diagram. takes up too much space. Oh, I need to go back to this for a second. So the weird thing about this is how many valence electrons does iron have?
Two
Two.
for 4s.
So a common charge for iron is plus 2. Another common charge for iron is plus 3. So if it's plus 2, what happens is the oxidizer comes along and it plucks these electrons first, the 4s electrons. And so these are the valence electrons. The 3D are actually considered inner shell electrons, or core. However, it's not filled, it's partially filled, so it's subject to attack. If the 3D were filled, then it'd be less subject to attack because it would be more stable. However, the oxidizer is still going to try to take electrons. Which electron do you think is going to be easiest to take from the 3D? Yeah, the negative 1/2, right? Because it's paired, and electrons share the same charge. And so probably if the oxidizer is successful, for sure it can pluck these first two off without too much difficulty. And then it comes along and tries to pluck the third off. And if it's strong enough, it can. And it's going to take the negative 1/2 electron here because it's paired. And so the two common charges for iron are plus 2 and plus 3. Now, it could try to take one more electron off, but it's going to be more and more difficult, because the higher charge plus 4, plus 5, plus 6 becomes extremely unstable. And so we kind of top out about plus 3 for free ions.
Which you get plus 8 in theory.
Yeah, in theory we could get plus 8 if we take all of them, but that would require an extremely powerful oxidizer, and so we're just stripping the entire shell, this shell, right? The fourth shell. We'll strip the entire thing off. Yeah, iron plus 8, you'd need something so powerful, and unfortunately that something so powerful doesn't really exist, and so it doesn't completely lose it. I mean, even like when we get manganese plus 7, yes, it's plus 7, but it's not really because, there's some covalent interaction there too between the manganese and the oxygen and permanganate. And so it doesn't completely let go. It's still hanging on. Yeah, it shares partially, but we call it a plus 7 oxidation state nonetheless because it tells us, if the oxygen could take it, it would be plus 7. Iron in the plus 8 oxidation state, we don't see it. Otherwise, it would be extremely powerful oxidizer.
Would iron really plus 8 decay within a matter of like nanoseconds because it's so unstable?
Well, it has something to take electrons from. It has something to take electrons from, yeah. But it'd be so highly charged. All right, then that's called the orbital energy level diagram. Then we have something called the orbital box diagram. The orbital box diagram saves us a lot of space. And so therefore, most of the answers in the solutions manual are going to be written like this. But what they don't show are the relative energies. So the orbital box diagram for iron would be 1s2, and then 2s, 2, and then 2p, 6. That is, there's a total of 6 electrons in the 2p subshell. And then 3s2, and then 3p6, followed by 4s2, and then 3d,
3d5.
no, close, 3d6. 3d6. All right, this is the orbital box diagram. It takes up less space. But what takes even less space is what we call the electron configuration. Electron configuration is a lot more compact. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. The superscripts just tell us how many electrons are in that subshell. And then we have the condensed electron configuration. Condensed electron. Or here, what we do is all the way 3p6 fills the argon. So first shell, second shell, third shell, argon. And then 4s2, 3d4. The fourth shell doesn't quite fill out. So we lay that. This is filling order. Sometimes we flip it to put it in order of reactivity. And so what we do is we write argon 3d6 4s2. And so if we write it like this, then we do this. We say all the electrons up to the valence are core, inner shell electrons, and then we show the valence. And so in this way, we can write the highest numbers on the right. Even though it doesn't fill this way, we don't fill the 3D for the 4s. But when it comes to reactions, the 4s are going to be taken before the 3D. So it's the opposite order of filling here. And so we'll just put it in numerical order because that's the order that the electrons are going to be taken away from the atom. That's not shown here because it doesn't go that far. So let's take a look. We talked about off valve. What was off valve?
Ground state fill.
Yeah, fill the lowest, right?
Yeah, fill the lowest ground states
Right.
first.
Right. We talked about off valve. We talked about poly. We talked about what's that other one? And one more.
Heisenberg?
For filling electrons. We did talk about Heisenberg.
Tons.
Tons.
Tons, right.
Tons.
So let's take a look at these. What are they asking for? Which of the following orbital diagrams are equivalent to each other? Well, is this one okay? A. Is that okay or not okay?
Yeah.
It's okay because we don't know, spin up, spin down, we don't know what's upside down or right side up. So this is fine. This follows Hund's rule as well because this, and it doesn't matter which of these three are equivalent. How about B? Is that okay?
No.
That violates what? This doesn't violate poly actually. This violates something else. It doesn't violate off valve either.
Do you think it's Hans?
Hund's rule. This violates Hund's rule. Yes. And so B we wouldn't even consider. That's wrong.
Hans is out.
C, is C okay?
Yeah.
Yeah, C is fine. No problem with C. In fact, A and B are going to be equivalent in terms of energy. How about D?
No.
No, D violates Hund's rule.
Again. Well, B and D are violent.
Does the following orbital diagram for a neutral species correspond to a ground state or an excited state? Well, one thing we have to say is that these rules are for the ground state, the lowest energy. But is this okay to have for an excited state? This cannot be the ground state. Why? Because this would violate poly. Does this violate poly? No.
we know off ground state.
Well, everything I've been talking about is for the ground state so far. But this one violates Hund's rule, right? Right. So this cannot be ground state because the P, right? But this might be an excited state. It might be an excited state because we're going to have an electron spin up that got ionized. But that would also be weird. It would be weird because if we're going to ionize an electron, would we ionize a single electron or we would ionize a paired electron? A paired electron. And so this is kind of weird. But we have no choice. This cannot be for the ground state. So it must be an excited state. And it's a weird excited state because of that.
When you were mentioning valence electrons, between 4s and 4p, right? Since they would both be 16 away, which one would be the first to have
The P.
The P?
Yeah. P are less penetrating than the S.
Yes, yeah.
That's it. And so we would do that.
All right.
The S orbitals are the most penetrative.
Yeah. S and then P and then B. All right, so these are some electron configurations, and here they're using the abbreviation here to save space. And most of these are just as you would expect. However, there are some ones that aren't as expected. And so we'll take a look at those. In fact, it came earlier. Yeah. And these the people just typically memorize. It also depends on the position. And so the two that are classic that you just have to memorize, and it goes for the same family, are chromium and copper. Chromium and copper have the predicted one, 3D4, 4s2. Do you see they reversed it? This is not the filling order. This is the taking order. So it's probably easier to see in terms of the energy level diagram. The energy level diagram is going to be the most informative. And the electron configuration is going to be the least informative. And so what we'll do is let's just look at the energy level diagram. I'm not going to write the first shell, the second shell, the third shell. I'm just going to write argon for the first three shells. Okay. And then what comes after the third shell? 4s. 4s2. And then 3d. And 3d4. And then the 4 P's are empty. This is what we predict. However, what's observed is something else. Yeah, right. And so what's observed is an electron gets promoted from 4s to the 3d. And so we end up with only one electron in 4s, and that electron gets pushed up into the 3d. The 4p are too high in energy to do anything, and it's not worth it. And so what we end up with is this. We predict this. We predict argon, 4s2, 3d4, or it depends. This is how you fill it. Or if you're looking at valence, then we call it argon and write it in numerical order. And so all the orbitals are written in numerical. That is 3d4, 4s2. If there are more orbitals, then we just do it. Over here, in terms of filling order, it'd be argon, 4s1, 3d5. Or in terms of leaving order, it's going to be argon, 3d5, 4s1. This is for chromium.
Is this an exception to Hund's rule?
No. Hund's rule applies for both. This is fine for both. This is an exception to
Polys.
not poly.
Off-bands because 4s in the ground state is not being filled.
What was it?
Off-band.
Not off bend. Close. Off bow. Yeah, this is a violation of the off bow. Off bow says we fill the lowest energy orbitals first. We aren't. We're filling, well, partially. It's a partial. We got the 4s, one. The second one should have gone there. And the reason this is observed is this. There's additional stability in half-filled and filled D subshells. Filled and half-filled have additional stability. So, if we have this half-filled here, and when you add up all those d orbitals together, it forms a sphere. And so the subshell, in fact, if you add up all the p orbitals together, it forms a spherical, what we call spherical symmetry. And if we add up all the d orbitals, it forms spherical symmetry. But what I'm going to do is I'm going to do it like this. I'm going to look at it as a cake. And if you have half a cake, you know, how do you normally slice it?
Into fourths.
Yeah, normally you slice it like this. And you get half the cake. And this half you can give to somebody, this half you can eat or whatever. However, this is not how this is sliced. It's not sliced in half like that because then it would be lopsided. When we look at this cake, the way it's sliced is like this. So when we have half a cake, it retains its spherical symmetry. And so that spherical symmetry gives it additional stability in terms. So if we remove half the cake here, then we still retain the spherical symmetry by adding up all the d orbitals. Versus over here, we have a half a cake here, and so we're going to slice it so we retain the spherical symmetry. Like this. And so I'm going to remove half of it off the top. It's still spherical symmetry. But now I'm going to remove 1/5 of it. And so I'm going to take a slice out of here. If I take a slice out of here, what does that do to the symmetry? It screws it up. And so now I have a lopsided cake, and it's not going to have that additional stability given by the symmetry there.
Does this special symmetry only exist for chromium and copper? Or does
Well, it's going to have the biggest impact for D. In fact, it's going to have the biggest impact for, chromium and copper. Yeah. It's the same thing, but as the atom gets bigger and bigger, then, if you lose a slice like this, it becomes less and less significant because this cake is so gigantic. The orbitals are growing much bigger. As we go 3D, 4D, 5D, that kind of thing. And so these are more dense orbitals, and it's going to be more significant. And so this is the reason. This is observed. And so what people do is they just memorize this. This is an exception. However, if we go from chromium, what's the next element after chromium? Manganese. Okay, then we ignore it. Manganese is just going to be normal. Manganese is going to be one more electron. Where are we going to put that one more electron? Here. And so this is what manganese is going to look like. But let's go the other way. Let's go to vanadium. If we go to vanadium, then vanadium is 2 electrons short of being half filled. So for vanadium, should we promote both s electrons? It turns out that's too much. We can promote only 1 electron. We can't promote 2 electrons. So vanadium is just going to have to be 4s2 3d3 vanadium. And so it's just one glitch there. And then there's one more glitch as we go across. And that one more glitch corresponds to copper. So when we go to copper, copper should be 4s2 3d9. And then this should go, oh, that's only 1 electron short of filling the D subshell. And so what do you think is going to happen here?
this is going to promote?
Yeah, it's going to promote. And so copper we predict is 4s2 3d9, but it's only 1 electron short, or 3d9 4s2. It's only 1 electron short And so what we're going to do is we're going to promote this 4s electron and fill the entire D subshell. And so rather than D9, it's going to be D10. Now D10 is special. D10 is not very reactive, once we fill that. However, what are the common charges for copper?
1 and 3.
Copper no. Copper is not 1 and 3.
3 and 4.
No, where is it on the periodic table? What group is it in? I don't like this periodic table that much because it's less informative. I like the more informative periodic table. Let me show you the more informative periodic table. Oh,
Is it +1 +2?
yeah. +1 and +2. What's going on with my search here?
So you currently in site tabler.
Oh, that's one.
I think there's something up with your search feature.
Thank you.
Yeah, I know how to search it.
Um,
I think your Google is automatically going to Journey, which is a different mode of research.
oh, okay, thank you.
So if you click the little button next to periodic table to the left of it. Oh, you can't. All right, then you probably have to just use the top URL bar.
Anyway, yeah, it's 1 and 2. 1 and 2 are the common charges. It's +1. Officially, it's +1 because how many valence electrons does copper have? 1. So it's a pseudo group 1 element. So pseudo group 1. Is it pseudo group 1? However, +2 is the most common charge. So +2 is going to have how many electrons in the D? So if we lose the first electron, is going to be lost from the 4s. The next electron is going to be lost from the 3D, which is going to give us 3D9. So that's weird. And so copper we have is argon, 3D10, 4s1 in the leaving. And so we lose an electron, we go to copper plus. Copper plus is going to be argon, 3D10. And it should stop there because 3D10 is filled subshell. It should be stable. However, one more electron gets pulled off. So we go to copper 2 plus. This is minus an electron. This is minus another electron. Copper 2 plus turns out to be the most common, but it screwed up our symmetry. Now we're at 3D9. So I don't have that perfect spherical cake anymore. So it's all screwed up. And so why would copper do that?
Because it's a full shell. There's the S shell. And I pulled both of them off.
Can it demote some selection?
No, the reason it does this is weird. It seems to be unusual. And the reason it's unusual, it has to do with something called ligand field theory in Chem 1B, which will tell you why the D9 is preferred. It turns out when you bond it to things, then it turns out to be lower in energy in a D9 than in a D10 configuration. That's because it tweaks. When we bond this, we lose the degeneracy between the D and it tweaks all the orbitals. And so this isn't what you would expect based on what we've been talking about. All right, so that's copper and chromium, and the other members of the family also have this weird thing going on as well. So is this okay for our orbital box?
No.
No, this violates what? Hans and
Hans and Polly.
Polly. B, is that okay?
No,
No,
That violates
Polly. Or,
no, Hans rule.
Hans rule. C?
yeah.
Yeah,
That's
it's good.
good. Yeah, that's good. You know what element this is?
That's
Phosphorus.
Yeah, it's phosphorus.
This is phosphorus. C? I guess I already talked about it. D? No.
No,
This is going to violate tons. This is off with the ground state. E?
No.
No, this violates. No, this doesn't violate Hund's rule. Hund's rule looks good. This doesn't violate off-bound.
Poly.
This violates poly. Look at the 3S.
Yeah, it's
Those two are going to have the exact same set of 4 quantum numbers. That's a violation of poly.
plus 3.
Those come from.
No, it's plus 1.
Yeah.
Okay, we already talked about that.
Yeah.
All right. The easiest way to get electron configurations, especially for complicated ones, is to use the periodic table. So let's try some off the periodic table. Let me see. Yeah. Let's go to, how about uranium? Let's try uranium. We're going to try to get the electron configuration for uranium element number 92. But this one, you're okay to use the condensed electron configuration. So from 92, we're going to work backwards to the nearest Nobel gas. Because the nearest Nobel gas is going to tell us this. So for example, radon is going to have a first, second, third, fourth, fifth, and sixth shell is going to be filled. This is the sixth shell. The shell's always been given with the S. And we don't even need, we need the pyramid for determining higher energy, empty. But here we can get it, the filled ones. And so it goes 6S, and then what's the next orbital? Now, this is kind of weird, because look at the number. Once we go 6S, we're at 56.
So it'd be 6S4.
And then where's 57? 4F. And what happened was there wasn't enough room to put the D, not the D, these are the D's, but maybe the F.
The inner transition.
So there wasn't enough room to put the F's there without making the periodic table look weird. And so it's going to 56 and then 57. So it's going to go 6S1, 6S2, and then 4F1 through 14. It should be 14. Let's count. So 4F 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. Can we have an odd number of electrons in a shell? No, what's going on there? What's going on there is there's a missing D. There appears to be a missing D element here. I have hafnium, but isn't there another D element here?
71.
Yeah, and that's element number 57. Which one is element number 57? LA. LA is what element? Lanthanum? Sure. Lanthanum. That, there should be maybe a Los Angeles CM, because you know what element 97 is? Berkelium. So we need a Los Angeles CM.
What about California?
Yeah, that's California. Yeah.
Which one might be the most funny?
Just, yeah, LA talking about make it in UCLA. Although, you know, the interesting thing is, the guy who discovered berkelium is not named Berkeley. The guy who discovered berkelium is Seaboard. And he has an element named after him, Seaboardium. Seaboardium. But, you know, he's a UCLA alumnus. And so every year he'd go to UCLA. So actually I've met him once at UCLA when he came to visit.
What's the best element on the entire table? Americanium.
Yeah, that's good. I like it. Californium, that's good. I like that. But anyway, element number 57 is actually lanthanum. And so and 57 belongs here. So this is why there's 15. This lanthanum doesn't belong in this block. Do you see the F block? Do you see the border here?
Yeah.
That's accurate. Because this element does not belong in the F block. This element belongs in the D block. And so the way we do this is like this. 6S1, 6S2, 5D, 1, 4F, 14, 5D, 2 through 9. And so we do 5D, it's split this way. It goes 5D1, 4 is 14, 5D 9. So that gives us a total of 10 5D. Okay. So that's how we use the periodic table. Now we're trying to get uranium. Uranium is no element number 92. So what we're going to do is we're going to start off with radon at 86. So we go radon, 7s,
So that's one.
2, yeah, 1, 2, 6D, 1, 5F, 14. Oh, no.
As I say, you've gone way too far.
Way too far.
Yeah,
5F, 1, 2, 3, and then we're done. So we use the periodic table to get the more complicated one. This is another section, but we don't have to memorize it. We just use the periodic table to get it. And then when we split it, like for example here, we split it to 5D1 and then an additional 5D9. So what most people do is they'll just condense it into 5D10, because that would be a filled subshell.
We have 1 minute.
1 minute. So maybe we might have a little bit of chapter 9 on Monday, because chapter 9 deals with shielding and penetration and some of the properties that we have in this. So, and the practice exam 3 has problems from chapter 9 on that. We might do one, atomic size or something. But anyway, I'll talk about it on Monday.